Hello everyone, I am Behnam Dezfouli. In this talk, I will be presenting our work titled Accurate Identification of IoT Devices in the Presence of Wireless Channel Dynamics. So what exactly is IoT device identification? Simply put, it's the process of automatically identifying the types of devices connected to a network by analyzing the network traffic. But why does this matter? Well, as more and more devices get connected, we need new ways to manage and secure them to meet both user needs and service requirements. There are some clear benefits to identifying IoT devices. For instance, if we know what type of devices are on the network, we can apply security techniques like microsegmentation. This lets us isolate less secure devices, helping to reduce the risk of security breaches. Another key benefit is traffic management. Based on the type of device, we can prioritize network traffic to improve the user experience. For example, devices that require timely delivery of data, like surveillance cameras and motion detectors, can be given higher priority, while less important devices, like wireless displays, can be assigned lower priority. Now let's briefly look at some of the existing approaches for IoT device identification and their challenges. First, there are traditional methods like relying on MAC addresses to identify devices. However, this approach has significant shortcomings. For one, MAC addresses generally only reveal the manufacturer of the device, not the specific type. Additionally, with the introduction of techniques like MAC randomization, identifying devices using their MAC addresses has become even more unreliable. Another option is analyzing layer 2 through layer 4 headers or even packet payloads. While this method can provide more detailed information, it comes with a major drawback, that is compromising user privacy. To identify devices, all communication patterns would need to be analyzed, which can reveal sensitive information. Not to mention, this kind of analysis requires significant computational power, which can be a challenge. Lastly, there is the approach of analyzing layer 2 features, such as inner packet durations or packet sizes. This method has the advantage of being more privacy preserving since it doesn't require deep inspection of the communication itself. However, its accuracy is highly dependent on network conditions. For example, if there are multiple devices communicating at the same time, the packet intervals can be affected, which in turn can lower the accuracy of identifying IoT devices. In this work, we address these shortcomings by proposing a layer 2 based device identification method. To overcome the challenges posed by channel dynamics, we introduce a new approach that provides fine-grained modeling of channel utilization and its impact on the collected features. This ensures that our method is more robust and accurate. Our results show that while using only layer 2 features gives a maximum device identification accuracy of around 75%, incorporating wireless channel dynamics significantly improves this accuracy to approximately 97%. In this work, we define device latency as a layer 2 feature. Measuring device latency is quite easy. For instance, it can be directly measured on the Wi-Fi access point or using a packet sniffer. In the diagram, we show an example where a Wi-Fi access point sends a probe packet to an IoT device. For instance, this probe packet could be a UDP packet sent to a closed port on the IoT device. After the access point generates the probe packet, it has to go through the process of channel access contention before sending the packet. Once the device receives the probe, it generates a response, performs its own channel access contention, and then sends the response back. It's important to note that the response time of the device is influenced by two main factors: the hardware and software characteristics of the device itself, and the level of channel utilization. Therefore, this response latency has the potential to be used as a unique identifier for IoT devices, especially if we can accurately account for the impact of wireless channel dynamics. To better understand the variations in device latency and the impact of channel utilization, we built a testbed that includes various types of IoT devices. In the testbed, machines 1, 2, and 3 are used to generate different levels of background channel utilization while the IoT devices communicate with the access point. At the same time, a packet sniffer collects the device latency of all IoT devices in response to probe packets. These probe packets are TCP SYN and UDP packets that are generated by an application running on the access point. These probe packets are sent to the closed ports of IoT devices to generate immediate reply packets. It is also worth mentioning that it is not necessary to generate probe packets locally by the access point or another device in the network. Instead, the access point can measure device latency for those packets that require immediate response from the IoT device. For instance, when an IoT device is communicating with a local or remote server, the access point can measure device latency for those TCP data packets that require instantaneous reply from the IoT device. In this paper, we focus on crafted probe packets by the access point. Before we present the results, it's important to note that instead of using a sniffer, the application generating probe packets on the access point can measure the time interval from T1 to T7. However, as we discuss in our paper, these measurements can be influenced by factors like the processing load on the access point. In the paper, we show that packet generation and protocol stack processing times can vary depending on the utilization of the access point's processor. Therefore, for more accurate device latency measurements, it's crucial to take these measurements within the MAC layer of the access point or by using a sniffer. Specifically, we need to exclude the time intervals between T1 and T2 from the device latency measurements to ensure that the latency is not affected by the access point software stack. In this presentation, we will focus on the scenarios where either the access point's MAC layer or a sniffer measures these intervals. Therefore, all the device latency measurements presented in this work represent the time intervals between T4 to T6. This figure highlights two major observations. First, the device latency in response to probe packets varies significantly across different IoT devices. Second, these response times also change based on the level of channel utilization. The key question we face here is how do we accurately model the effect of wireless channel utilization on device latency features? A major challenge in accounting for the impact of channel utilization on device latency is that channel utilization is measured over a period of time rather than as an instantaneous value. Therefore, we cannot rely on the channel utilization values measured and reported by Wi-Fi network interface cards. To address this problem, we propose the concept of accumulation score as a method to measure the instantaneous occupancy of the wireless channel and its effect on the exchange of probe response packets with IoT devices. The basic idea is to measure how packets exchanged close to the probe and response packets impact device latency. As this figure illustrates, we need to assess how the packets exchanged around the probe and response packet pair impact device latency. We categorize the packets sent before the response packet transmission as predecessor packets, shown in green. Similarly, the packets sent after the response packet are referred to as successor packets, shown in orange. Here, our main objective is to quantify the impact of these predecessor and successor packets on device latency. For a given probe response pair, the accumulation score is based on the properties of the predecessor and successor packets exchanged around it. The proposed accumulation score takes into account several factors: the distance of these packets from the response time, the duration of the packets, as well as the number and frequency of the packets. For example, as shown in this figure, packet E has a greater impact on the accumulation score than packet D, and this is because packet E is closer to the response frame and is also longer in duration. In the interest of time, I won't go into the mathematical details of how exactly the accumulation score is calculated. Instead, I will focus on the basic ideas and how we model the impact of each predecessor and successor packet using the mapping method shown in this figure. To account for the impact of each predecessor or successor packet on channel utilization, we consider the relative distance or time difference of each packet from the response packet. The closer a packet is to the response packet, the greater its impact on device latency. To represent this relationship, we use weight functions that peak at the time of the response packet's transmission. The weight function is used to measure the effect of each predecessor and successor packet on the accumulation score. For instance, the weight of packet P1 and its contribution to device latency is calculated by its corresponding point on the weight function. Therefore, using different weighting functions, we can assign different weights to predecessor and successor packets. For example, as shown here, when we use a bell curve, packets with similar distances from the response packet receive similar weights. In contrast, when you use a gamma curve, even if a predecessor packet and a successor packet are at the same distance from the response packet, the successor packet is given a lower weight. In this work, we use the bell curve weighting function. We use various methods to empirically evaluate the effectiveness of the accumulation score in enhancing device identification accuracy. In the first set of experiments, we aim to understand the relationship between accumulation score and device latency. For this purpose, when we were collecting data in the testbed, we generated various channel utilization levels from as low as 0% to 100%. Then we mapped the entire range of channel utilization values to 3 accumulation score ranges. So each of these accumulation score ranges here map to a range of channel utilization levels. In this figure, we present the distribution of device latency in 3 ranges of accumulation scores across all the IoT devices in our testbed. As the accumulation score increases, we observe a corresponding rise in device latency. This further validates the effectiveness of using accumulation score to represent channel utilization. To demonstrate the impact of channel utilization and accumulation score on device identification accuracy, we use the LGBM machine learning algorithm. We trained the model within predefined accumulation score ranges and then assessed its performance across different accumulation score ranges. More specifically, we trained the model using data from one range and then tested it on the other 2 ranges. For instance, for the results presented in the leftmost figure, we trained the model using the data collected when the accumulation score was within the range 0 to 0.1, and then we tested the model using the data collected when the accumulation score was within the other 2 ranges. The results presented here show that when the algorithm is trained exclusively within a specific accumulation score range, the F1 score consistently falls below 75%, with some instances dropping even as low as 25%. This trend persists even as we increase the size of the training dataset. This reveals a significant limitation here. Algorithms trained on data from a single channel utilization range or a single accumulation score range struggle to generalize effectively when applied to device identification tasks across different channel utilization ranges. Essentially, the model learns and recognizes patterns within the narrow confines of its training range. As a result, when faced with channel utilization levels outside this range, the model's ability to accurately identify devices diminishes. Simply increasing the dataset size within the same accumulation score range does not solve this issue, as the model is not exposed to the broader variety of patterns that occur at different channel utilization levels. Interestingly, we observe a relative improvement in accuracy when the algorithm was trained using the middle accumulation score interval, the range 0.1 to 2. We attribute this enhanced performance to the overlap of channel utilization samples from both the lower and upper intervals within this middle range. This partial exposure helps the model better understand device behaviors across a broader spectrum of channel utilization ranges, therefore allowing it to generalize more effectively beyond its primary training intervals. To further validate the importance of using the accumulation score for device identification, we evaluated the performance of the LGBM algorithm when trained on the entire accumulation score range, but with different sets of features. For the first set of results, we used TCP-based probe packets, and for the second set, we use UDP probe packets. For each set of results, the first row shows the set of features without using accumulation score, and the second row includes the accumulation score. These results confirm that even when the model is trained across the full range of accumulation scores, including the accumulation score as a feature consistently leads to improved F1 score. Moreover, the accumulation score proves particularly useful when some latency features are restricted or when the number of samples is limited. For example, in situations where only UDP features can be used instead of TCP, we see significant performance improvements. Here, with only 5,000 samples, we observed that using the response to high payload UDP packets results in 67% accuracy, but when we add accumulation score to the feature vector, the accuracy increases to 73%. In summary, these results show that using the accumulation score enhances accuracy for all TCP and UDP based features. Next, we measure the accuracy of various models when trained using the entire dataset, which consists of around 125,000 samples. In each iteration, we use 20% of the dataset for training and the rest 80% for testing. The results here show that the decision tree model has the lowest accuracy, while the LGBM model achieves the highest accuracy. The right figure here shows the training and inference time of various algorithms when measured on an ARM Cortex-53 processor. This processor is used by some of the new off-the-shelf Wi-Fi access points. The results show that the decision tree model is the fastest to train and has the shortest inference time, making it a suitable solution for resource-constrained scenarios. However, there is always a trade-off between computational efficiency and classification performance. When comparing LGBM and XGBoost, both achieve similar F1 scores, but for resource-constrained devices like access points, the algorithm with lower overhead is preferable. In this case, LGBM outperforms XGBoost in terms of efficiency. The efficiency comes from LGBM's use of histograms to represent data distributions, which reduces memory overhead and minimizes the processing required for intermediate results. This makes LGBM particularly beneficial for devices with limited resources, such as home Wi-Fi access points. In summary, this presentation highlighted the importance of accurately identifying IoT devices as a critical step towards improving network security and management. We demonstrated that device latency as a layer 2 feature can be an effective tool for IoT device identification. However, channel utilization has a significant impact on the accuracy of latency measurements. Machine learning algorithms that do not account for this impact struggle to accurately identify IoT devices in dynamic wireless environments. Without considering channel utilization, the device identification accuracy remains below 75%. To address this challenge, we introduced the accumulation score, which captures instantaneous channel utilization and its effect on device latency. By ensuring the training data covers the full range of channel utilization values and incorporating the accumulation score into the features vector, we were able to achieve an accuracy of over 97%. Finally, we demonstrated that this proposed method can be implemented on off-the-shelf Wi-Fi access points or even on a low-cost packet sniffer, making it a practical and scalable solution for IoT device identification. Thank you.